Have you ever wondered how scientists determine the water content in a substance or the amount of nitrogen in organic compounds? Well, you're in for a treat today. We're about to embark on a journey that traverses the fascinating realm of chemistry, exploring some of the most vital techniques that chemists employ in their day-to-day work. These include Karl Fischer Titration, a method used for precise water content determination, Kjeldahl's method, a technique used for estimating organically bound nitrogen, and last but not least, Oxygen Combustion Flask techniques, a method used for elemental analysis. Each of these techniques, while seemingly complex, unravels a unique aspect of chemical analysis, aiding in various scientific endeavors and even in industries. So if you've ever been intrigued by the science that goes on behind laboratory doors, you're about to get a peek into that world. Ready to dive into the world of chemistry? Let's begin with Karl Fischer Titration. Karl Fischer Titration sounds complex, right? But it's not as intricate as it seems. This method, named after the German chemist Karl Fischer, is an ingenious technique to determine the water content in a substance. That's right, it's all about water detection, but why is this important? You might ask. Well, the presence of water, even in trace amounts, can significantly influence the properties and quality of many substances. So, knowing the water content can be crucial in many industries, such as pharmaceuticals, food, and petroleum. Now let's delve into the principle behind Karl Fischer Titration. It's based on a chemical reaction where iodine reacts with water. This reaction is in the presence of sulfur dioxide and an alcohol, usually methanol, to form a neutral compound. The amount of iodine consumed in this reaction is directly proportional to the water content, allowing us to measure it accurately. The beauty of this method is that it only reacts with water and not with other substances, making it highly specific. So, how do we perform this titration? We start with a sample of the substance whose water content we want to determine. This sample is then dissolved in a suitable solvent, such as methanol, in the titration vessel. We then add the Karl Fischer reagent, which contains iodine. As the titration proceeds, the iodine reacts with the water in the sample. When all the water has reacted, any further addition of iodine changes the color of the solution, indicating the end of the titration. By knowing the amount of iodine used, we can calculate the water content in the sample. Remember, the accuracy of Karl Fischer titration depends on careful sample preparation, meticulous titration, and precise measurements. But once you get the hang of it, it's a straightforward and reliable method to determine water content. So that's how we determine the water content in a substance. Now let's move on to Kjeldahl's method. Ever wondered how scientists determine the amount of nitrogen in organic compounds? The answer is Kjeldahl's method. Let's dive into this fascinating process. Named after its inventor, the Danish chemist Johan Kjeldahl, this method has been a cornerstone in the world of analytical chemistry since its introduction in the late 19th century. Its primary use is to measure nitrogen content in organic and inorganic samples, making it an invaluable tool in fields like food and beverage analysis, environmental testing, and pharmaceuticals. The principle behind Kjeldahl's method is quite straightforward. It involves converting all nitrogen in a sample to ammonia, which is then quantified. Sounds simple, right? Well, let's dig a little deeper. The process begins with digestion. The sample is heated with sulfuric acid, which breaks down its organic material and transforms the nitrogen into ammonium sulfate. This step also requires a catalyst to speed up the reaction, typically a mixture of potassium sulfate and copper sulfate. Next comes distillation. The digested sample is made alkaline using sodium hydroxide, which converts the ammonium ions into ammonia gas. This gas is then distilled off and collected in a solution of boric acid. Finally, we reach titration. The ammonia in the boric acid solution reacts to form ammonium borate, which is then titrated with a standard acid. The amount of acid used gives us a direct measure of the nitrogen content in our original sample. However, Kjeldahl's method isn't without its limitations. It can't measure nitrogen in nitro compounds, azo compounds, or nitrogen oxides. But despite these constraints, it remains a widely used and dependable method in analytical chemistry. So there you have it, a quick tour of Kjeldahl's method. From its principle to its step-by-step process, we have covered the basics of this important technique. But remember, the world of chemistry is vast and ever-changing. And Kjeldahl's method is just one piece of the puzzle. Now that you're familiar with Kjeldahl's method, Let's explore the oxygen combustion flask technique. Oxygen combustion flask technique might sound like a mouthful, but it's a crucial method in chemistry. Diving into the heart of this technique, it's all about one thing: combustion analysis. This is a process used to determine the elemental composition, specifically carbon, hydrogen, and nitrogen, of an unknown substance. Now you might ask, why is that important? Well, by knowing the elemental composition of a substance, we can deduce its molecular structure, which is a big deal in chemistry. Let's break down how it works. The principle behind the oxygen combustion flask technique is simple, yet fascinating. A sample of the unknown substance is burned in the presence of excess oxygen inside a combustion flask. The combustion process breaks down the substance into its elemental components, which then react with the oxygen to form water, carbon dioxide, and nitrogen oxides. Now onto the step-by-step process. First, the unknown substance is weighed and placed into the combustion flask. Then, an oxygen-filled balloon is attached to the flask, providing the necessary excess oxygen for the combustion process. The flask is then heated until the substance is completely combusted. The resulting gases are collected and analyzed to determine the amount of water, carbon dioxide, and nitrogen oxides produced. This data is then used to calculate the elemental composition of the original substance. What's truly amazing about this technique is its versatility. It's not limited to just one type of substance. It can be used for solids, liquids, and even gases, making it a powerful tool in the chemist's arsenal. So, there you have it. The oxygen combustion flask technique is more than just a mouthful. It's a fundamental method that allows chemists to unravel the mysteries of unknown substances one molecule at a time. Knowing these techniques opens up new perspectives in understanding chemical processes. Let's summarize what we've learned. These techniques may seem complicated at first, but once you understand the principles behind them, they become much clearer. Let's take a moment to recap what we've learned today. We kicked off this journey with Karl Fischer Titration, a method that has proven to be an accurate way to measure water content in a sample. We learned about its two main variants: colorimetric and volumetric titration. The former is useful for samples with low water content, while the latter is used for samples with higher water content. But remember, the key to successful titration lies in understanding the sample and choosing the appropriate method. Then, we plunged into the world of Kjeldahl's method, a classic technique used to determine the amount of organically bound nitrogen in a sample. We broke down its three main steps: digestion, distillation, and titration. Digestion involves the conversion of organic nitrogen to ammonium sulfate. Distillation then converts this to ammonia, which is subsequently titrated to quantify the nitrogen content. While it may seem like a lot of steps, each one plays a crucial role in ensuring accurate results. Our exploration didn't stop there. We dived into oxygen combustion flask techniques, a method used to determine the carbon and hydrogen content in a sample. This procedure involves the combustion of a sample in an oxygen-filled flask, leading to the formation of carbon dioxide and water. These are then absorbed and measured to determine the carbon and hydrogen content. The beauty of this technique lies in its simplicity and accuracy. Indeed, these techniques are like pieces of a puzzle, each unique yet interconnected in the grand scheme of chemistry. They serve as powerful tools for scientists and researchers, helping them uncover the secrets hidden within samples, be it water content, nitrogen content, or the carbon and hydrogen composition. We've covered a lot today, but remember, practice makes perfect. So keep exploring, keep learning. There's a whole world of chemistry out there waiting to be discovered. And who knows? You might just uncover the next big thing. Chemistry is filled with fascinating techniques and methods that help us understand the world around us. As we've seen, Karl Fischer Titration, Kjeldahl's method, and oxygen combustion flask techniques are just a few examples of the wide range of tools at our disposal. Each of these techniques offers a unique insight into the complex dance of molecules and elements that define our universe. They help us measure, analyze, and comprehend the intricate chemistry that underpins everything from the food we eat to the air we breathe to the water we drink. Remember, every technique we've discussed today is a stepping stone in the vast journey of scientific discovery. Stay curious. Keep experimenting. Each experiment you conduct, each result you observe brings us closer to a deeper understanding of the world around us. I hope this video has stirred your curiosity and helped you understand these techniques better. Subscribe for more because you won't find me later.